So I guess we'll start. It's a very happy day to have Zhuo defending his thesis. Zhuo says he started here in 2008. He started working on this 60 gigahertz networking project in 2010. He got a job in 2013, and he spent the last 2 years kind of part-time meeting us to write one chapter after the next in order to kind of understand, the goal of the thesis was to understand and build some algorithms for the Mac and for the routing in these small 60 gigahertz networks with sort of very highly directional antennas. In any case, I'm really glad that we've arrived at the end, and even though Zhuo will hurt our departmental average, I think that for how many years to graduation, I'm better this year than next year. Very good. Please.
Good afternoon, everyone. So my name is Zhuo Chen. Today I'm going to present my PhD work about 6 gigahertz Mac and network design.
Yes, sir.
First, I will introduce some background knowledge about 6 gigahertz. Then I will show some the Mac protocol design, and also introduce my work about some network design for the 60 gigahertz network. First thing is why I want to start the 60 gigahertz network. That's because I think back to 2008 or 2009, the FCC has allocated a large amount of unlicensed spectrum for the 60 gigahertz, and also followed by the other country worldwide. So in general, the 60 gigahertz will have 5 to 7 gigahertz bandwidth. So as we use in today's Wi-Fi about in the 2.4 and 5 gigahertz, so the bandwidth is less than 1 gigahertz. So another thing to trigger the research interest in the 60 gigahertz network is there's a big breakthrough for the CMOS design technology that can enable the low-cost 60 gigahertz radio device. And nowadays, because of the 60 gigahertz can easily achieve very high data rate communications, so there are many applications for the 60 gigahertz. For example, it's like the various transmission of the Blu-ray radio, and also there are some industry want to use the 6 gigahertz for the small cell backhaul, for the backhaul network. And there is some unique propagation property of the 60 gigahertz. The first thing is because the free space propagation loss is scaled as the square of the wavelength. So the 60 gigahertz will perform 21.6 dB worse than the 5 gigahertz. But luckily, 6 gigahertz can use the direction tuners. So we found that if both the 60 gigahertz, the transmitter and receiver use direction tuners, for the same aperture size, so actually the link of the 6 gigahertz can outperform by the 5 gigahertz link by 21.6 dB. There's another unique propagation property of 6 gigahertz is there's a very high penetration loss. So because the 6 gigahertz wavelength is so small, so it cannot diffract around the human and small furniture. And if a human stands between the transmitter and the receivers, the link budget of a 6 gigahertz will decrease by the 20 to 30 dB. So that means that link may be broken. So here is the system model we used to study the 6 gigahertz network. For example, if all the nodes will be in the quasi-omni mode if they are idle. And we assume there is neighbor discovery protocol. So each node will know the antenna direction of each neighbor. And we also use directional RTS and CTS packet. For example, if node A wants to transmit a packet to node C, it will first point to the node C and send a RTS packet. And node C.
Quick question. So when you say A points to C, how does it actually do that? That has a map with coordinates, or there are beacons that needs to be tracked, or there's channel estimation that needs to be measured?
Yeah, I think there are the two kind of solutions. First is there is some existing work about a neighbor discovery protocol. It's kind of like each node will do the scanning and find the direction of its neighbors. And I think in the another 60 GHz standard, like in the 822.11ad, it will use the beamform training packet. For example, like the RTS and the CTS maybe become a beamforming packet, and after the several rounds of the beamforming training, so the node A can know the direction of the node C and can remember the kind of like the antenna direction.
So for your work, you assume that's done something.
Yeah, that is done something.
You took care of that.
Okay, fair enough.
Yeah. And then the node C will point back to node A and send a CTS packet. So after the and node A and node C will point to each other and transmit data and acknowledgement packet. And after that, the node A and node C will go back to the quasi-only mode. So there are several research challenges of the 60 GHz network. First is about the MAC protocol design, because I will introduce later the widely used CSMC based protocols in the 2.4 and 5 GHz have something is not efficient for the 60 GHz. And also because use the direction tuners, there is no omni broadcasting in the 60 GHz. So this become a challenge for the routing protocol design. And the other thing is like a good routing protocol should also utilize the high spatial reuse of direction tuners, so which is not considered in the traditional mobile and ad hoc routing. And also we have mentioned that the 60 GHz link is easily to block by the human body in the network. So a good routing protocol should also handle the link outage, like if some people is moving in the network and some link of the network is be blocked. And here is the summary of the contribution of my PhD work. First, I propose a enhanced directional MAC protocol for the 60 GHz, and this is a low control overhead protocol, and it can achieve lower delay jitter and significant higher capacity for the network. And based on the proposed MAC protocol, we also start the routing protocol of 6 GHz. We propose several routing protocols to exploit the spatial reuse of the direction tuners. In particular, we propose two routing algorithms to enhance the single path routing. And we also propose a dynamic node-disjoint path discovery process to enhance the multi-path routing in the 60 GHz network. And in the end, we start the characteristic of pedestrian blockage in the 60 GHz network, and we propose a two-part solution to improve the TCP throughput of the TCP flows. First, I will introduce about the MAC protocol. So there's called a definite problem, which was introduced by the CSMA-based protocols for the traditional directional MAC. For example, if node A and node B, they both have packet to transmit to node C. So node A may start the transmission first. So it will send an RTS packet to node C, and then node C will send a CDS packet back. Because of the direction antennas, so node B does not know that node A and node C are talking to each other. So it thinks maybe node C is idle. So it will send an RTS packet to node C. But because node C is pointed to the node A, so it's cannot aware of that communication. So this packet was kind of finally be dropped. And then the node B will start a backup process. So this backup will be smaller because it's the first time of the backup. And after the backup process finished, the node B will transmit another RTS packet. But the node A and node C may still like talking to each other and transmit the data packet. Then this packet will be lost again. In this time, for the traditional CSM-based protocol, the node B will start a much longer backup. So there were two cases. The first case, like if node A, it has another packet to transmit. It will transmit after a very short period of backup. Therefore, if node A grabs the channel, it will have the advantage over node B to grab the channel again. So there will be cause some like short-term unfairness problem. So which will increase the jitter of the flows in the network. In another case, if node A do not have a packet to transmit, because node B is in a very long backup, so the channel will be idle for that a long period. In that way, the channel utilization caused by the deafness problem will become really low.
A question again. So when everything was idle and A transmitted the request to send,
Yeah.
C has no way of knowing that request to send is coming from that direction. So its beam can be pointing nowhere.
Yeah,
so
it's in the
you cannot
yeah.
assume you have
Yeah.
both transmit and receive antenna gain. And so I think it's crucial whether you assume that it was still able to detect or not. Because if it's not able to detect by not having pointed the antenna to something that still didn't happen, then terminal B has no way of being heard either, even if C was idle. So it seems that there is an underlying assumption that the request to send can be heard even though C has not yet pointed the antenna to either A or B.
Yeah, if node C is in the quasi-omni mode,
Yeah.
and if node A is point to node C and transmit a packet, the node C can hear it.
Right, so that's a crucial
Yes,
assumption.
right,
You
yeah.
just lost 20
Yeah,
dB of your
yeah.
link budget,
Yeah,
and you're assuming it still works.
But he has to design the RTS to accommodate that.
Right, I'm just saying, I mean,
Yeah,
so,
exactly.
yeah.
Yeah.
Right.
Okay.
But
So it's
the next effect-
either 20 dB louder, or takes 100 times longer, or something.
Yeah.
Yeah, because also the RTS packet is can be transmitted very slowly. Like
Notice it's
yeah.
not trivial, because 20 dB, I don't want to belabor the point. You know, it's 100 times the watts, it's
Yeah.
out of the question.
Yeah.
So then it has to be 100 times longer, which has the latency implications.
Exactly.
Question, what's the power consumption when you are in the omni, on the quasi-omnidirectional mode? What's the, when you are listening, when C is actually trying
Yeah.
to listen to, is that
I think both the transmitter and the receiver is the 10 million watts.
both?
Yeah.
Okay.
Yeah, it's, the only difference is the antenna gain. Like if you use direction antennas,
Right.
it has much higher antenna gains, and in the quasi-omni, the antenna gain is really low.
Yeah.
So is the power consumption, that's a pretty good question, is power consumption the same when it's in quasi-omni mode versus when it is actually pointing at someone and decoding at high rate?
Yeah, the transmission, the power consumption is the same.
The same.
Yeah.
Well, at
Not
this kind of
very,
level,
right?
probably the power consumption is dominated by baseband processing, not by the radio power. You're talking 10 milliwatts.
10 milliwatts.
So then the lights are consuming more than RF or processing.
I would have thought, honestly, once you make a beam, they both beam form and you have a high-speed connection, right? The work C is doing to decode packets, right? I would have thought then would be a lot higher than when it's sitting in quasi-omni. But I don't actually, we didn't, I don't know.
I have a more top-level question with this question. So how much mobility do you assume from the nodes, or are they going to be rather stable? So fixing the antennas and such. So I guess the question is, what is the use case? What are the nodes would be in your network?
Yeah, for example, like if in future, like my laptop will connect with this projector, use a 6 GHz network. So there will be no HDMI cable connect with your Blu-ray player and your TV.
Okay.
And also, like if you use the PS4, right, it's also the gaming. It can directly point to your TV. But the problem is like because the 6 GHz has the cannot diffract between the small object. Like if I'm like if some people is working off the link will be broken. So that's why it's like we also start the link outage of the 60 GHz network.
So I guess the answer is it's not very mobile.
Yeah, it's not very mobile. And another use case is a small cell backhaul is also kind of fixed.
Yeah.
So in your protocol, are you giving yourself the opportunity that if the shortest path gets blocked, you could reestablish communication by picking up the same signal but of a reflection or some other direction? And how would you find those other directions?
Yeah, I will talk about later about the routing. We did have the multi-part routing. We handle this kind of the link outage problem. And there is some existing research about the solutions about in 2.4 and 5 GHz. So the basic idea is like they want to add the global control information so that every node can know the status of others.
But by the way, the problem you just presented is no different really than the classic hidden node problem. It's just made worse by the fact that the antennas are not listening in all directions.
Yeah, it's a kind of exaggerate of
Right.
the hidden terminal problem. And the RTS cannot solve the problem because RTS becomes directional
too.
Yeah. So the idea is like they want to add some, like for example, in some work they want to use another omnidirection antenna to do the omnidirection RTS CTS to solve like the kind of the deafness problem. But all these solutions have some problem in 6 GHz because we have mentioned that the antenna gain of the quasi-omni pattern is really low. So in that way, it's like a node cannot broadcast global control information. And if they want to kind of like do the directional control message, it will bring too much overhead into the network because every packet it needs to talk all its neighbors one by one. So in this way, we propose called enhanced direct MAC. We call it Dmacc. And here is how the Dmacc works. If node A and node B want to talk to node C, they will use the same contention window size. And the contention window size will be told by node C in the acknowledgement packet. And there will be no exponential backoff will be used in the MAC protocol. And if node A and node B want to transmit a packet to node C, it will always use the same contention window size. So the challenge is like how we can find the optimal contention window size. So like in the CSMA network, we know that if the contention window size is too small, there will be too many conditions in the network. And if contention window size is too big, there will be too many idle periods in the network.
But if you could just go back a little bit. So since there is no backoff, then how do you solve the multiple access problem? Do they still transmit randomly on top of each other, or they somehow coordinate?
Yeah, they still choose randomly, but they will use the same condition window size.
So you're back to the classic problem of they can bang into each other and
Yes.
bang into each other and back to each other
Yeah,
forever.
yeah.
Which is
But-
why the backoff was invented.
Well, no, there's a distinction between the back off and the exponential back off. So he backs off, he has a fixed back off. and he
Oh, I
chooses-
suppose it's
But
exponential.
so
Oh, okay,
it's
so it's a little
doubling the
milder.
back-off window
Okay, I get you.
and-
There's still
and
back off, but it's not
dynamically.
exponential.
Right.
Okay, all right.
And it's like later on in our analysis, we found that the optimal condition window size is only depends on like how many nearby transmitters. So we have several consumption to develop our capacity model. Like we assume like there will be n transmitter to around a receivers from different directions, and we also assume the beam width is really low. And we also assume we use the saturated traffic model. And also we, in the analysis, like in the traditional CSMA network, MAC protocol, we use memless assumption. So that means the two transmission, the interval between two transmission is exponential, it follows the exponential distribution. And
What's saturated traffic?
it's
Full
like,
buffer, right?
yeah, full buffer. It's like a node always has a packet to
Percent.
transmit.
Okay.
Always meant, yeah.
And we got some idea from the old work from the Clay Rock and Tobagi. And they have found that the throughput or the capacity of the network is depends on the length of the, is defined by the utilization of the period of the network divided by the sum of the busy period plus the idle period. So for example, like the utilization period is the period that for the data communication. So actually that should be related with the throughput of the network. And the busy period is contained two parts. One is like if a contention happens, and the other case there will be a contention-free period after 2 points point each other. So the busy period is considered two parts, and the idle period is marked in the yellow, and it's basically is like no one transmit in the network. And the detail like the how to how to get the length of each period is in the dissertation, and I do not list the detail here. But this is finally we find that if we want to achieve the maximum capacity of the network, the optimal condition window size will be equal to like in equation 1. And it's really interesting that it only depends on the how many number of like active neighbors of a node. So in that way, we do some like model validation in NS2 simulators, and by use this system parameter, we will find that the optimal condition window size is close to the 6n minus 1. N is the active neighbors of a node. And we use the uniform circular antenna array with 16 antenna elements. And in that way, the mean low beam width is about 9 degrees. And here is the propagation model we use in our simulation. And we first start the single hop scenario. In that scenario, it's like there will be n transmitter located on a circle with a radius r. And there will be no collinear node, and there will be like no transmitter can sense other nodes transmission. And we also use the CBR traffic over the UDP. And here is the result of the simulation and the analysis. And we can see that if the condition window size is bigger, so the analytic model and the simulation result are quite close to each other. But we can see that when this is the figure on the left is there are two transmitters in the network, and on the right there are 9 transmitters in the network. But the only problem is like when the condition window size is really small, so the analytic model and the simulation model there are a big gap. So that is because we in our like analysis we assume like the exponential inter-arrival. So actually, like if the condition window size is small, so the transmission interval is not the exponential. So that's why like our analysis model is not has some problem when the condition window size is small. Yeah. But when there are 9 nodes in the network, the optimal condition window is equals to about like 53. So in that way, we can see that it's like our model is quite fit.
So if I understand correctly, the terminals need to somehow learn what's the number of terminals that are in contention so that they can use the right window size.
Yes, yes.
Okay.
Yes.
And after they do that, we have achieved something that appears to be upper bounded by 50%, which is kind of magic. But besides, maybe you can explain why the 50% later. But my question is, given that we're starting to coordinate, at least at minimum by sharing this one number, which is the number of terminals in contention.
Yeah.
I can imagine, and you're going to accuse me of being old, but I am old, so I may allow myself that. If I know the number of terminals in contention, I could advertise a TDMA window with n slots. Now,
Yeah.
and after the overhead of having advertised that, and perhaps a little extra for deriving timing, I can push utilization to 90% of that.
Yeah, yeah.
So as we start coordinating a little more, does TDMA becomes a little more attractive?
Yeah, maybe you can say like in our in the future work we did mention like the TDMA maybe also be used in the Dmacc protocol. But the problem like for the 6 GHz, if you have some like link blockage, right, the TDMA has some problem because you need to kind of like do this kind of scheduling, and if the link is broken, you cannot do any like the scheduling, the control message. So in that way, like if the network is quite static and there's no link blockage, as I imagine like if the ATT they want to have the small cell solutions, maybe they will use the TDMA solutions. But in our like the local area network, there may be some people moving and the link is broken. So I believe the CSMA kind of like condition-based like Dmacc protocol may still work better than the TDMA-based protocol.
Thank you.
And here is like how to measure the jitter of the flow. So first we define the delay of each packet between the time receive a packet and the time of the transmission time divided by minus the transmission time. And then we define the jitter is between the difference between consecutive delays. And from this is simulation result is about the single hop scenario. So we can say that although the throughput is not much higher than the like basic directional Dmacc protocol, but we did achieve like much smaller jitter as shown on the right, no matter like the network is saturated or not. So
what's the difference between basic and enhanced? Enhanced is your protocol, right?
Yeah, it's my
So what's basic?
Basic is like some existing solution in 2.4 GHz.
And what's the difference?
The difference, like they use exponential backoff. Yeah.
So the main advantage of not using the exponential backoff is the jitter reduction
Yeah, that is for the single hop scenario.
for the single.
Yeah, single hop scenario.
And also, I guess, the actual throughput, right? Because with the exponential backoff, given that everybody is in hidden node problem,
Yeah.
the throughput would,
it's
one user would hog the channel.
Yeah. So it's kind of like not too much when the throughput increase because this is single hop scenario, and especially like when the network is not saturated,
Yeah.
so they perform the same.
But I don't think you're tracking fairness here. I guess you have a huge advantage in fairness.
Yeah, I
Because
think
with
that,
exponential backoff, the one that gets through to the base.
yeah, we,
Delays them.
We'll
we-
keep it. We'll keep it until the buffer
yeah,
is
yeah,
empty.
yeah,
or
yeah, we measure it from the like jitter.
Okay.
Like if you grab channel for the longer time, then you
I
lose
see.
the channel, then the jitter will
Will
become
be
much
much
bigger.
larger. Okay. So
Yeah.
indirectly, you are tracking fairness through
Yeah,
jitter.
yeah,
That makes
exactly.
sense.
And then we start the multi-hop scenario. So because, as mentioned before, the line of sight link may be easily blocked by some obstacles for the 60 gigahertz. And we design this topology, assume that there will be no interference between like each links. And we also use we start both the UDP and the TCP traffic. And here the result is like, on the X-ray, it's x-axis is the number of hops of the multi-hop chain. So we can say that the proposed Dmacc, the throughput, no matter use the TCP or the UDP, the throughput is at least 25% higher than the traditional basic Dmacc. So by using our proposed MAC protocols, we start our research about the network protocol. First, I will talk about the single path routing in the 6 GHz network. So,
Can you explain a little bit high-level motivation for the multi-hop? In the past, whenever we talked about multi-hop, which of course in academia is very, very popular,
yeah.
it turns out that most deployment scenarios that we are aware of involve going into the internet and surfing or going to some app. And so the one node that has the network connection very quickly becomes the bottleneck.
Yes.
And so
yes.
all the advantages of multi-hop kind of disappear because that node throughput is divided
Yeah.
by everybody else. So,
Yes, yes.
so unless you have in mind some application that escaped me that is peer-to-peer,
Yeah, I think
in brief, where would you see a multi-hop being used?
the multi-hop is required in 6 GHz because sometimes, like, if the link between you and me is blocked, so we need to find a relay node. Otherwise, the communication is permanently blocked, and that is like one big reason.
Okay.
Yeah. So because the property of the 6 GHz link. Yeah, and also later we will show that, like, because we have direct antennas, actually in the ad hoc networks we can achieve like much higher throughput than if we use only direct antenna network because we have the spatial reuse. So less interference between different flows. So here is an example, like on the left is the minimum hop count routing, which is widely used in the traditional, like the mobile and ad hoc networks. And on the right is a node disjoint path. So that means if there are two flows in the network, so each node will use the different, like, choose the path that has no overlap with no overlap nodes. So we both show that if we use omnidirectional network, we can say that actually if you want to use no disjoint path, it's perform worse than the minimum hop count route because there's no like spatial reuse, and one path is choose the longer path. But the thing is much different if we use direct antennas, because if the two flows, they use different node disjoint paths. There's no interference between them. So each node, just like each flow, can transmit it simultaneously. That's why like the aggregated throughput is almost double of the throughput of the minimum hop count routing. So that gives us some like motivation, like if we can find a good routing protocol that could like fully utilize the high spatial reuse property of direction tanners. But the problem is like the node disjoint paths may not existing if there are too many flows in the network. So we think that we want to find something is called the fattest path routing. Someone also mentioned it's called the widest capacity routing. So like we first assume like have some assumption about the bandwidth of each links. We think like because we find that by use our enhanced directional map and also use the round robin scheduling, we can say that it's the bandwidth of a link is determined by like how many active links associated with the node. For example, like if there are 3 active links associated with this node, so everyone gets 1/3 of their bandwidth. And in this scenario, like this will become the bottleneck of the network because there are 4 active flows. So each flow can only get like 1/4 of the bandwidth. So based on the bandwidth of a link, we can also define the capacity of a path. That is, the link on the path has a minimum bandwidth. For example, in this one, it's like both the flow 1 and flow 2, the capacity is only 1/4. Although the link bandwidth of this link is 1/2, but there's a bottleneck here. So the first flow, the bandwidth, the capacity is also 1/4. So based on this, we want to each flow, they want to find a path that has a maximum capacity. We modify the existing Dactyl algorithm to find the fattest path. So here is a given example. Like for example, there are 2 flows in the network, so which are joined one after another. So the first flow is from node 0 to node 7. And in that case, like if all the paths at that time is the fattest path, no matter like because there's no traffic in the network. For example, in one scenario, this node maybe choose this really longer one because they only know they want to choose the fattest one. And then the second flow, when they join the network, they say, oh, there's like no better choice, so this is only the best choice. In that way, it's like all these 2 flows, they get 1/3 of the bandwidth. So that's, in the next slide, that's the problem of we only consider the fattest path. So we can say in these four cases, so in the last slide, we show the case 4. So for the fattest path routing, the first flow is can randomly choose a path because all the paths is fattest. So it's maybe in case 2, or in the case 3, or the case 4. And based on what the decision made by the first flow, if the second flow runs the fattest path routing, it will choose the fattest path based on the first flow. So the first case is we use the shortest path routing, and the second case is also the route can be found by the shortest path because node 0 thinks this is shortest path, and node 0 thinks, oh, this is shortest path. And in the result, we can see that if we want to only use fattest path, we cannot always outperform by the shortest path algorithm because the fattest path it doesn't consider the hop count. So this motivates us to combine the fattest path and the mini hop routing together. So basically, we propose two heuristic algorithms. First is like we consider hop count first. We choose the k shortest path algorithm for example, in our simulation, we choose 100, the first 100 shortest path. And among these 100 shortest paths, we choose the fastest one. The second heuristic algorithm is like we run the fastest path algorithm for 100 times. So that will give us several like the fastest path. Then among these fastest paths, we will choose the path with the minimum hop count.
No question. So it makes a lot of sense, very common sense approach to take. At the same time, I'd be curious to explore the parameter space. So I can imagine if the network is very, very small, as maybe a few sensors inside the home, then I can just enumerate all the paths and pick the best by whatever criteria. Just enumeration works. If the network can be large, but perhaps the sensors only transmit a very short packet if an event happens, and they're mostly idle all the time. So since the network is very lightly utilized, then whatever shortest path is still okay. So when does a better routing algorithm starts to become an important ingredient? I imagine the number of nodes has to be above a certain minimum to make it interesting, or the network utilization has to start getting loaded so that. Do you understand the trade-off?
Yeah. Because we started this problem because like we most focus on the TCP flows. Because nowadays, like in the internet, like almost like 85% of traffic are TCP flows. TCP traffic is always they want to like some video application, like they always want to achieve the highest throughput. So not like a sensor network, it's like they just like use UDP, they send one packet and they send another packet. So for the like, as I mentioned, like 6 gigahertz may be used for like some application. It require like higher data rate. So that's why like we focus on the TCP traffic, and like so for the like if there's not so much traffic in the network, maybe I think maybe either path it doesn't matter. And this is the simulation topology, and we use this simulation topology through all our works. And we first place 15 nodes on like 50 by 25 grid, and then we randomly shift each node by a distance randomly from a randomly interval from 0 to 5 meters, and also a direction from like 0 to 360. So this will be generate like random topology. And then we show some result, like if there are like 5 TCP flows in the network, each from node I to node 49 minus I, and we randomly generate 5 topologies, and we find that like on average, both heuristic algorithms like increase the capacity of the network a lot, because this like routing algorithm they consider like the spatial reuse. So that's why it's like both algorithms achieve like much higher capacity. And after we start the single path routing, we are consider like another scenario is like the multi-path routing. And here is some like simple case like I have mentioned, like in 6 gigahertz network, maybe the link between the source and the destination may be broken. So we may need to choose a relay node in the network in order to send a packet to the destination. So there are several solutions. For example, this is a traditional solution. It's both the source and destination, they will choose the same relay node. So they will transmit all the TCP data and ACK. And here is another, because there are 2 relay nodes. And the second solution is like the case is the source use one relay node to send the data packet, then the destination choose the other relay node to send the acknowledgement. And then we can further extend this scenario. It's like, for example, the source, because it's node, there are two relay nodes. So for each packet, it will just flip a coin and randomly decide if I should transmit the data packet to this one or the other one.
Question. If the obstacle that was between the source and the destination
Yes.
moves to the source and R2, for example,
Yeah.
just walks across
Yeah,
that dot,
yeah.
and you already initiated the TCP flow, right?
Yes.
So what happens with the application, or is it, do we have to find another route?
Yes.
And we
Yes.
send,
Yes. Yeah. Yes. That will be talk about in the link outrage sections.
okay, got
In
it.
that way, we handle the link outage.
Okay,
Here we just, like in the other scenario, maybe source and destination, they are too far from each other. So
Okay.
they had to choose the relay node.
okay.
So, yeah. So this is both the source and the destination, they are randomly toss a coin to choose like which relay node they should choose to transmit each packet. So we can say that like for these three cases, if we use omnidirectional antennas, there's no throughput increase, and like surprisingly, like for these three cases, the throughput decrease. That because there will be, in this scenario, there are only 3 nodes that are contained in the channel. But in these 3 cases, there are 4 nodes that are contained in the channel. So actually, the throughput is decreased because there are more nodes, more contention. But the story is much different if we use the directional MAC protocol. And we can say that if the source and the destination, they choose the multipath to send a packet to the destination, they could like increase the throughput by almost like 50%. And we can also say that in this multipath routing scenario, it's like our Dmacc is perform much better than the directional MAC because we can optimize this condition window size. And based on this, we propose a dynamic node disjoint multipath routing for the 60 GHz network. And the key idea is like we extend the existing dynamic source routing and to do the route discovery. And the basic procedure is the source node will initiate a route discovery process, and in that process, it will find multiple paths from the source to destination. Then we use an algorithm to choose the node disjoint path to transmit the packet. So there are many challenges to discover like multiple node disjoint paths. The first thing, as I mentioned before, because you use direct antennas, you cannot do a broadcast. In the omnidirectional antennas, I just broadcast the route request, and all my neighbor will receive it. So that is one difference. The other thing is like we also want to find like more node disjoint paths in the network because we have this kind of special reuse, like and also we do not want to induce too many overhead message in order to find this node disjoint path.
So there's an interesting angle here, perhaps for future work. Your point of view is kind of higher up computer science, I would call it. Either you're connected or not connected, and you might be connected to more than one.
Yeah.
I think you can still build into that something that comes motivated from the physical layer, which is between any 2 nodes. You may have more than one connection by pumping the antennas whether to the shortest path or to bouncing off a wall, and so you may make a list of k different paths that are possible. Now, if the 2 ends don't move, maybe they're always there, and by one gets blocked, you call to the second best at some capacity penalty.
Yeah.
So I think it introduces an angle that is coming from physical layer or even propagation, and may provide an interesting twist.
So his original thinking was motivated by the belief that in a building you can have hundreds of devices.
Yeah.
You don't have need to have a centralized AP-based architecture.
Right.
So it could, and since capacity is sufficient, can pay the multi-hop penalty.
Right.
But Ronaldo, I think is making a good point, that in fact, you can have coefficients for your beamformer that I find
Yeah.
another path to you, and I actually have a bigger space. I can route to you via DAN, or I could route by a reflection off the wall.
Right.
And you could actually optimize over that choice. Yeah.
I mean, I think your framework can be extended very easily because you would call it a passive relay,
Yeah.
where it's just an object that you're bouncing off at some capacity penalty.
So what's the feasibility of multi-beam antenna? Is that
Oh, very high, very high. I mean, I switched myself, you'll remember some of the meetings, I was very skeptical a couple of years ago.
simultaneous?
And what's happened is that the semiconductor guys, whether silicon or silicon germanium, are producing arrays of 16, 32, all integrated with the antennas included in the wafer. It's pushed by the millimeter wave imaging at 90 gigahertz for airport radars, airport imaging devices. 70 because of vehicular-to-vehicular, but coming probably very soon to 28 as well. So we can talk, I don't know about hundreds, but in the more common sense of 18, 30 element, and which with each element having a few dB, so you build up significant gain with each array. The more interesting question is, can you serve multiple beams simultaneously,
Right,
as in
that's what I was
multi-beam,
asking.
or you have a single RF? So you would, but even with single RF, right? You can build this table of different directions, and still point to one out of K,
Yeah.
under the assumption that the environment is stationary, and if any one gets blocked, you go to the second best, or you go back to the very best. I think we're still far off from sort of generalized MIMO, where every RF chain is fully controllable, and you just estimate the channel and load the network with the
So
maximum
we're far
spatial
off in
diversity.
the sense that it can be all in one ASIC, kind of far off. Like,
Right.
I mean, conceptually,
Conceptually, math is easy.
It's-
Yeah, no,
it's-
implementation-wise, yeah.
And to to solve this challenge, so we first, like in the discover scheme, we need to emulate a broadcast. So we have like 3 ways to emulate a broadcast. The first one is like we can send the route request packet to each beam direction, one by one. The other we call the neighbors web is like send each neighbor one by one. So because we already know the neighbor, we can have an enhanced feature is like we can transmit a route request to a neighbor several times until we receive acknowledgement. So that's an advantage if we have a neighbor table. So and another thing is like if we want to find like multi-paths from the source to destination, so we should try to forward this route request while mark through different paths to the destination, so that each node in the network can forward can have a different scheme to forward a route request. It may just forward the first route request is received, or it may forward the route request received from a path that is like come from a shorter path than all route request it had received. So another like general solution is like a node may forward a route request received from path that is not longer than all previous route requests it has received.
So another very interesting adjacency is that in the RF community, some of us that move from skeptic to believers is because it's very likely that we can make a discrete set of directions work. So say 16 fixed directions.
Yeah.
And I have a single RF that I can switch among the 16.
Yeah.
So then I do have a route discovery, but I would call it direction discovery. So I may have 8 by 8 set of directions, only 64. If I can assume somehow synchronization, then I can just sequentially measure all 64 and maybe find out what are the top strongest. According to some minimum performance, maybe I have 3 that are viable, and then I put it in memory. So this could be, like in your case, 3 routes that are viable, which happens to be 3 combinations of angles.
Yeah. We can have a code book. Right?
Yeah,
So
right.
kind of
And so there are pattern
remember
matrices, there's other structures that are likely to be very efficient as implemented as discrete set of directions,
Yeah.
as opposed to just fully controllable phase shifters and magnitude controllers.
Yeah, exactly.
Yeah. Okay. But I think the parallel is interesting because you could treat them as just routes
Yeah.
that are available to you.
Yeah. And the destination will reply all the route requests to the source, and so it's the source can discover multipaths from the source to the destination. So after the node finds the multipaths from the source to the destination, we propose a low complexity grading algorithm to select the node distron path from the multipaths discovered. And for each packet, the source will randomly choose a path from this node distron path set and then send it to the destination. Because we use the source routing, so it just puts the route into the source header, and then this packet will be routed to the destination. And we measure several we have several performance metrics to do the performance evaluation. So we want to measure how many number of route requests transmit in the network. We do not want to introduce too much overhead to discover too many paths. And also we want to find as many paths as we want. And also especially important, we want to find the node distron path. So if the algorithm only give me 100 paths, but only one node distron path, so that is also not useful. So we have 3 different the route request transmission scheme. We have also 3 route request forward schemes. So that gives us 9 combinations. So and also it shows us how many route requests.
So when you say beam sweep, can you expand a little more? So
Yes, yes.
you're assuming a beacon is being pointed at one direction and then it goes around 360 degrees?
Yeah, for example, in this work, the beam width is 9 degrees. So in order to cover the 390, so we need to more than 36
Okay.
beam directions.
And then you end up with a problem of dwell time, right? Because there's going to be an estimation problem. In order to decide whether the beam is there or not there, you need to integrate n of SNR. The more directions you have, the less SNR per direction.
Oh, yeah.
So the longer it's going to take. So that's why it's a little tricky to do sweeping if you keep track of time and signal-to-noise ratios.
Yeah. So because in our simulation, we kind of use the code book. We hard code all the beam directions.
So I had the impression that this beam sweep was not by direction, but it was you had already run the algorithm to know where your neighbors are, and you pointed at each neighbor.
Yeah,
and
that is.
tried to send them.
Oh, okay.
Yeah.
So you sweep through predefined directions where you know somebody is
there.
there.
Oh, that's
As
Yeah,
opposed to
yes,
going
yeah.
around 360 in discovery mode.
That's 2 solutions. So one is called the neighbors web. It's we only send to each
To
neighbor.
the neighbor.
I see.
Another is unblind. I just want to cover all the 360. So later on we can see in this table. So actually the beam swap is introduced a lot of route request message in the network. As I have mentioned, for example, the first is the first only forward scheme should not be used because it can only discover one node distron path in the network. So that is not what we want. We also find that the beam swap, as you mentioned, is also not good. It's introduced too much overhead into the route request. Yeah, and also the shorter forward algorithm is also not good because it cannot find multiple notification paths. So therefore, like there is only 3 solutions left. It's like, but all 3 solutions it seems like pretty close, but we should be choose should depends on the scenario. For example, if the network is quite static, we should use the not longer forward scheme, because although it's introduced many like the route discovery overhead, but it can find a lot of notification paths. And if the network is static, we just do it once, so its overhead is not a big problem. But later, like if the network is dynamic, so we do not want to inject too many route discovery message in the network. In that way, the neighbor unicast and with the shorter forward scheme, it can find some notification paths, and it's much quicker, and it has fewer overhead into the network. So that is our like observation. And we use the same topology like using the single path routing. We find that like no matter there's only 1 flow in the network or there's a 5 flow in the network, on average is like the multi-path solution perform much better than the single path routing. So because it's like the single flow scenario has get more occurrence because there's no other like interflow interference. Yeah, and because there are some interflow interference, we do not consider in this paper. In the 5 flow scenario, we only improved 14% on average.
Question. So the work here resembles a lot, and I think DSR came from the
Yes.
ad hoc networking community. So it was really popular still maybe 10 years ago, and thousands of papers. And so I kind of would have expected that you would have compared also to some of the known protocols that were for ad hoc networking. So what's the decision to only compare single path and multi-path? So I would have assumed there was maybe 500 multi-path protocols as well, and something, or maybe I don't know. But, so.
Yeah, actually, like for example, like I mentioned like for this like algorithm for this first one, that was like for like in the directional dynamic source routing in 2.4 and 5 GHz, they did use this scheme, and we found that in this actually this is not a good scheme for the directional MAC routing protocols, because it cannot find the multipath route, and also it generates a lot of like overhead. The problem like in so that's why like we come with some like other like solutions. So we think like this combination will become better. Like in the field work, I have mentioned that we could even further propose some like further enhancement from like this table, and that is really good.
Right, but so let's say you would have used AODV. You know that?
Yeah.
So does it map to one of these alternatives, or would that be a separate comparison?
That should be a separate comparison.
And so to even further remove myself from the ad hoc community, can you summarize at a very, very high level, because we have directivity of the antennas, is there something fundamentally different to the multi-hop ad hoc protocols that people have been studying over a long time to make things work in these directive channels? And what would that be?
Yeah, the first thing is the high spatial reuse.
Okay, right.
Yeah, that is one. The
So a good
second-
protocol should give you much higher capacity because the beams are giving you that.
The second thing is like we show that something is special for the 6 GHz is a link outage.
Right.
Later on we'll show in the next section. it's like the link outage for the 6 gigahertz is much different than the traditional mobile ad hoc network.
So can we say at a high level that the graph connectivity matrix at high frequency is much more sparse than
Actually,
at
the
the
story
lower
like
frequency?
this. For example, in the mobile ad hoc network, so if like we are like keep moving, if the link between you and me is disconnected, it may never come back, right? Because we move to different direction and we move far away from each other, and we don't know like when we will meet each other again, right? But in 6 gigahertz, the link outage is become like the
Transient,
the,
very transient.
yeah, like the pedestrian. It's like people move across the link, it blocks the link. And after like a few seconds, it move away. And then the link between you and me is
Okay.
back.
So it's intermittent versus.
Probably I can, this is about the link outage. I will introduce in the next chapter. Like I have mentioned, like in 6 gigahertz, the line of sight link is easy to be blocked by the like pedestrian, the network. So the links in the network will be on and off frequently if we have the human mobility, not the node mobility. So actually the broken link problem is well started in the ad hoc network. And for example, like Yanni mentioned there, the DSR and AODV is like, if the current path is broken, it can quickly find another path. And also like because there's the TCP over mobile ad hoc network has some problem, a lot of people do a lot of work. Like for example, they have developed some like cross layer message to tell the transport layer like this link is broken, please do not restart the timer. And also there's another scheme like it's like called fixed retransmission time. So we do not need to double if we find a root blockage.
But it seems inherent that if we want to deal with in a network with a lot of link unreliability, we must start with some kind of design that has a lot of redundancy.
Yes.
Because otherwise, if I have just one link and it goes down, then I cannot even
Yes.
ask for help, right?
Yes.
So I need to have K paths, and then one down, and maybe one goes down, and then the issue is which one of the K-1 do I pick instead?
Yes. And also like you also need to make a decision, should we still use this path later or not?
Right.
And also
Yeah.
like another difference is like for the traditional mainnet, they do not use the TCP over the multipath because there's no special reuse. So they do not want to use that. But in our previous, we show that the TCP over multipath used in direct containers is working very good. So that is the solution we kind of like come up. So the link outage, as I mentioned, is quite different from the broken link in the mainnet. As I mentioned before, like a link broken by a blockage by a pedestrian may be recovered after a short period. And also the TCP flow over multi-route can improve the performance in a static network. We want to say like, how about like if in a dynamic network, right? And actually we first start look at the characteristic of a pedestrian blockage. We kind of started like two properties of a link blockage. First is like, what is the probability that a link will be blocked if people are moving in the area? And the other interesting property is like, if a link is blocked, how long this link will be blocked on average? So that is quite interesting. And we kind of use the widely used the random directional model with the bounce strategy, and for the pedestrian movement, that means like this scheme will generate a uniform spatial distribution of peoples in the network, and in this scheme, like each pedestrian, they make their own decisions, and they randomly choose the speed and direction, and independent from each other. And when this person hits the boundary of the area, it will change the direction, follow the reflection of the light. And here is two like our pedestrian blockage model. So this is the link, line-of-sight link between the transmitter and receiver. And here is the three scenarios, like if we model a people like a cylinder, and then if we project it to the XY array, it becomes a circle. So we can say that if the people is across the link, so this link will be blocked. So there will be several scenarios. And there is like, this scenario is like there is not blockage. We assume like if a people like is like across a transmitter or receiver, it will go underneath the receiver. So in that way, it will not block the channel. So it's just a assumption for the pedestrian blockage model. And we kind of find interesting that like if a people like in this region, we call it blockage region. This is transmitter and this is receiver, and this is the radius of the human body. And if the center of people are in this shaded area, so the link will be blocked. So because like we can see that if these people are in this area,
Yeah, I apologize, but I don't understand your diagram. So when you say transmitted,
yes,
if you go back one,
yes,
right? So is it a single point source at the transmitter?
yes.
And then what is the circle?
The circle is the human body.
Oh, okay.
Yeah, if the body
So
like
the transmitter and receiver are just the end point sources?
yeah, in the point.
And these are three different persons? That,
Yes.
that
really,
okay.
Yeah, if like
Three different people at different positions?
yeah. If the,
And you're saying only the middle is a blockage, the one on the left and the one on the
all
right?
these three are blockage.
All three are blockage?
Yeah, this is not
Okay.
blockage. Like if
It doesn't need to be three different people, it could be one person
Yeah,
walking through the
yeah,
path.
Yeah.
right?
yeah.
Scenarios, right?
Yeah,
Yeah.
any
So-
of this person will
Right, the
block
person
this.
doing that path, that trajectory, right?
Yes.
Yeah,
Now, but I still fail to understand your
yeah, the lower
icons,
one.
because a transmitter is still the point source at the center of that person. So how is the transmitter at the center of the person?
So I think what's confusing here is you've drawn a person as a circle. but
That
with a-
includes the
Oh,
transmitter.
No, but
yeah.
it includes a circle which is identical to a transmitter.
So
Okay.
Right.
I'm wetting the transmitter or something?
And it's not a transmitter.
Yeah,
So
it's
so
not
the
transmitter.
thing that looks like a
This is-
wheel with an axle in the middle
Yes.
is a person, and the center of that axle is not a
A transmitter.
Not a
transmitter.
transmitter, it's just the center of
Right.
the
It's,
person.
it's the center of the person.
We
Yeah.
reviewed these slides, and I said you need to make a slide that explains this. So
Yeah.
Okay, so what if you get rid of that? So in the upper case, there's a transmitter and receiver. That's the little circle that's not surrounded by
Yeah.
the big circle.
At the end of the lines.
Yeah.
Yeah.
And each one of those human cylinders is a blockage event on that channel.
Yeah.
Whereas in the second case, none of those human cylinders are blockages. So for instance, the one in the middle, he's not blocking the one
That
on the
is
side.
easy to understand. I don't
But-
understand why the left and the right are not.
So this
Yes.
question we've always had this controversy is if you're standing over the transmitter or if you're
Oh, if it's
exactly
above or below, because there's no
Yeah.
three dimensions
Right,
here. So
or is it
maybe-
inside your
okay,
body?
there's 3 dB,
So-
there's
so-
a height.
So you define it that way, that there's no,
Yeah.
that's not a blockage event.
Right.
Yeah.
Yes.
Right.
Well, we
Because
could have
you're assuming
defined
that
it the
the
other
eye-
way, that you're sitting on it, and
Right.
it's a total blockage
Yeah.
event.
Right.
But he chose this to
Okay.
say it's not.
Okay, I get it,
Yeah.
yeah. It's the z-axis that makes
Yeah.
that not being a blockage
Yeah,
event.
yeah.
Okay,
So now go to your next slide will now make sense.
okay.
So that gray area is all the places where the center of mass the center of a human cylinder, if it's located in that gray area, causes a blockage
Okay.
for those transmitter A, receiver B.
Yeah,
And there is like several parameters of this blockage region. We have the D is the length of the link, and R is the radius of the human cylinder, and also L is the parameter of the blockage region, and the S is the size of this blockage region, and we also have the A is the size of the area where people are moving, and also we have the number of people in the area. And also we have the average speed, like people are moving. And the first we come with a blocking probability model is from the probability distribution of a person location is uniform. So the probability that a person in a blockage region and block the link is S over A. S is the size of the blockage area, and A is the the size of the area. So if we have because each people are moving independently and follow the identical distribution, and when there are n people in the area, we can know that this is the blocking probability of a link. And then we come up with the second model. So if we think the blocking region of a link is act as a server with infinite capacity. So if the server will become busy if one or more people are in the blockage region. And also the probability that the server is busy is the same as the probability that the link is blocked. So we kind of transmit this problem to a queuing problem. And for the queuing problem, the most important parameter is the arrival rate and the service time, average service time. So we get a nice result from the old work from the Thomas, and it gave it said if rho is the density of the people in the area, and the boundary cross link of a line, which length is L, is only related with the length of this line and the density of the people in the network and the average speed of these people. Yeah, that is quite interesting. So in that model, we can get the people arrival rate into this area to this equation. And this is the density of people, and this is average speed, and this is parameter of this area. And also we can get the average service time from the little law, also explained in this paper. After we get the lambda and mu, then from the MI1 queuing theory, we can know the probability that a server is busy is by equation 3, and we get lambda and mu, we get this equation. And so if we compare these two models, actually if the blockage region is much smaller than the area size, actually these two models will get the same result if S is much smaller than A. So that means both models can be used. And also from the current theory, we can get the average length of a Bayesian interval. That is the average duration of a link blockage we want to get, the TB we want to get. So because we have the two blocking probability model, we can also get two models for the TB. And we can also similar if n multiply S is much smaller than the size of the area, the two model is kind of quite close to each other, and it can be simplified like this. And we do the validation use the same randomly generated topology, and for each topology we run 10 rounds, and each round will run 100 seconds. And we have different movement patterns for the people. And for the first two patterns, people moving with high speed. And in the third is people moving with, on average, has low speed. And in the first configuration, the people will have a pause interval. And in the second and the third configuration, the people will keep moving and will not pause. And here we draw a picture about the x-axis is the length of a link, and the y-axis is the link blocking probability. And we find that the link probability is increased linear as the length of the link become longer. So that is really heuristic. Like if the link is longer, then maybe actually it's increased linearly, as we both show in the analytic model and in our simulation model. And and when there are like more people are in the area, we also start a scenario like when there are like different number of people moving in the area, we can say that the average link blockage probability is quite fit. And it's interesting that it doesn't depend on the how fast the people are moving. It's the link blocking probability is only related with like the density of the pedestrian in the network. It doesn't related with like how fast the pedestrian are moving. And we found that like our model for the average link blockage time. So our analytical model is a little bit like this is for the different people moving in different speed, and our analytical model is a little bit underestimate about the simulation result, but it's quite close. And the trend is similar. It's like the average blockage time increase when the average moving speed increase. Like if people move faster, the link will be blocked shorter. And also like the average link blockage time increase slightly as the number of people increase in the network, but it's not as the slope is not as high as the link blocking probability. So it's kind of flat. So this is kind of quite interesting result. And
question on the results of the blocking events seem to be like worst case, right? Because if you interrupt the connection, right, just momentarily by basically moving your hand through it, right, you count it as a blocking event, right? If the person and then at the physical layer, that would probably be compensated somehow, right? It's not like it's a total blocking event if you are connecting, as you were saying, to the projector and somehow I just wave my hand, right? It's not a blocking event, right? I need to stay there, or, right? So this is kind of worst case, which is pretty good, right?
Well, so it's interesting. It's somehow his model is about humans at kind of walking speeds, right? And events like your hand, that's
Well,
a tenth of a second, 100 milliseconds. You could do
Right
a
now
lot
it
of
would
data
count
in
it.
100 milliseconds, but you'll be like, oh, maybe a hand is not a
No,
big
not a
enough.
problem.
Well, I think the
Object
deployment
is-
scenario that has a lot of influence. So we've been doing measurements in collaboration with the university in Chile.
Yeah.
And if your link is short and people are milling around, then what really matters is a person in proximity to the antenna. Because what matters is in proportion to the spot size. So you draw it as a line, but it's
Right.
really a beam.
Right.
Now, the beams are not really all that narrow. Remember, we're talking about 16 beams, so we're talking about beams of 10, 20 degree
Right.
beam width.
But
So
if
if you're
his hand
fairly
here,
close,
right? Yeah.
then like 2 shares away from your antenna, then I'm blocking all of it.
Yeah.
But the minute I move 20 lambda, 100 lambda away,
Right.
the energy has diverged so much that I am invisible. So I
Yeah.
think you're both right, depends on the actual deployment scenario.
Okay. Yeah.
By the way, what we also learned is that, and with students you can do this, so you can put 1 person, 2, 3, 4, 5, and the actual number didn't matter.
You
So-
are using students
Yes,
for
yes. So
and your IRB.
yeah, they're all very well under healthy conditions. Remember my question? In Chile, right? So the first guy produces like 25, 30 dB, but when you're in the lab with radio signals, 30 dB is humongous. The
Yeah.
second one is not going to get it down to 60 because now it's finding some other way.
Yeah.
So when we say it doesn't diffract, to a point.
Right.
So it's not cumulative.
Yeah.
Which is so I was happy to see that you took the approach here, either it's block or not block.
Yeah, okay.
But it's not
Yeah.
cumulative, block by 2, block by 3. It actually makes no difference. Once it's blocked, it's blocked.
yeah, exactly. Yeah.
Okay.
And we also extend to start the root blockage characteristic. We also, first we define the length of a root is the sum of the distance between each link on this root. And also the root blocking probability is defined by the fraction of time one or more links on the root are blocked. And this is quite interesting for the root blockage. When there are 10 people in the network and there are 30 people in the network, and we can see that it's also like the increase as the length of the root is increased. But we can see that the 30 people in the network is kind of the link root blocking probability is really high. It's like more than 50% the probability like a link will be blocked or root will be blocked if there are people in the network. So in the later simulation, we can see that we should use different strategy for 10 people and 30 people. Like our solution we can show later is like the solution better for the 10 people in the network. It's not good for the 30 people in the network. It's similar like in the mobile ad hoc network. It's like, for example, the DSR is working better when there are like low mobility in the network, but maybe LDV works much better when the node is moving faster in the network. So it's kind of similar. And we kind of propose like two solutions to mitigate the link outage problem in the 6 GHz. The first thing is like we introduce a blockage timer, because we have to know that the average length that a link is blocked, right? So in the traditional mobile ad hoc network, if the source finds the root is broken, it's just remove it from the cache. And after all the root is being deleted from the cache, it will start another root discovery to find another set of the roots. But here, like in the 6 GHz, we know that after a few seconds, this root will become maybe back again. So like why we delete that root, right? So here, like we introduce a blockage timer. Like when we detect a link blockage, we mark a label for this root. Like this root cannot be used for like 2 seconds, and after 2 seconds, we can reuse that root again. So actually, the blockage timer will introduce a trade-off between like how many root discovery were triggered, because we do not delete cache in the root in the cache. The other thing is like if we set the blockage timer is very short, right? So we are kind of trying to use the root that is blocked. So that is also not good. So this is why we need to have some analysis for the average blockage time. So we can set the length of the blockage timer is around that the average blockage time. And we also start the size of the root cache, because we know some result in the mobile ad hoc network is like small cache will perform better than a bigger cache, like when like the node moving faster in the network, because the root is become obsolete as time goes on. And we also want to use multipath routing, because we know that the multipath routing can utilize the high spectral reuse of the network, and we have approved that it works good in the static network. And we use the fixed retransmission timer scheme like in traditional like TCP over mobile ad hoc network to handle the root failure. And here is the result if there are 10 pedestrians are moving in the network. So we can see that like if we add the blockage timer and we use single path routing, we can improve the performance of single path routing a little bit. And if we employ multipath routing, we can have a much better increase of the throughput of the TCP flow. And if we employ two schemes together, so we can have like the 55% increase. So this, which seems really good. But unfortunately, like the result is not good when there are 30 people, 30 pedestrians are moving the network. As I have mentioned, like in the previous slide, is when 30 people moving the network, actually it's hard to find two non-destroying paths in the network because each route has the more than 50% probability that this route cannot be used. And also we see that like just like the mobile ad hoc network, when nodes are moving faster, when too many people are in the room, like the link outage will happen very frequently. And in that way, probably the shortest path with like smaller cache size will be the best solution when there are 30 pedestrians in the network. And at the blockage timer will not help a lot. And also the multipath routing will not help because we cannot find the multipath route from the source to the destination.
Question, what's the coverage area of the network?
55 multiplied 30.
55 what?
Meters multiplied 30 meters.
Okay.
Yeah. Here the conclusion in my work is like I first propose enhanced vector map, which solves the unfairness and the low channel utilization issues of the deafness problem in direct MAC protocols. And we combine the fastest path and the minimum hop routing together to improve the TCP flow when using single path routing. We also propose the dynamic no-disjunct path routing protocol that can further improve the performance of the TCP flows. And we also start the characteristic of link blockage introduced by the pedestrian blockage. And we also propose two solutions to mitigate the link outage problem introduced by the pedestrian blockage. So there are some like future work also as mentioned, like the TDM may be a good MAC solution if the network is static. Yeah. And also, like Yanni mentioned, like a new forward scheme maybe can propose to further improve the performance of the route discovery. And also maybe a learning-based protocol may be used to estimate the link blockage, so we can start it based on the learning. We can consider like the people moving their hand or something. It's kind of not by the analytic model, but we can have some learning model. And also like we found that the TCP, the end-to-end TCP protocol has some problem, like in the in the 60 GHz network. It's similar like the mobile ad hoc network. When the link on and off periodically, the TCP is not work better. So the hop by hop transport, like I think previous WinLab students have some work about this kind of like hop by hop transport protocol. That is a good fit for the 6 GHz network.
That will be below TCP, an alternative to TCP?
It's just replace the TCP.
Replace.
Yeah. So in the end, I want to thank my advisors and also the committee members and all the faculty and staff in the WinLab, and also thanks my friends and colleagues at WinLab. Thank you very much.